Okay, so let's start. So again, just a few reminders, announcements. Project reports are due this week. Actually, the same day, I think, that the current problem set is due. This time, actually, I request, I'm also going to put this on Piazza, send me email. Please send me email with this exact title, CS446, Project Progress Report, your user ID. It's going to simplify my life and increases the chances that you'll get feedback. And this is what you'd like to put in, you know. What you've done, what your plans are, how you've changed your original plan, and what kind of problems you have. Questions? Yeah.
So has the project feedback been sent out yet?
Just for select few of you. So most of you did not get feedback, no. That's hopefully that didn't stop you from working on the project. Yeah, hopefully you will get feedback on the progress report also. So, and all of you are welcome, many of you are using it, to come either in office hours or otherwise if you set up time and then talk about the project. We have an exam, the last meeting of the class, December 8th, which means that the week after Thanksgiving is the last week. Originally, I was planning to spend the last meeting for a review, and the question came up, do we need a review? Sounds like a rhetoric question. So the answer is yes. Okay. So, I mean, it's not going to change the material for the final if that's the issue. So I'm going to tell you what's the material, but I do want to get questions. So if you feel that there are some topics that you think should be reviewed, specific questions, please send me email, you know, short list of things that you think clarifications are needed, examples are needed. You can also send this or talk to the TAs in office hours or sections so that we'll use this time better. So please do it. We're going to put finals, example finals, before the end of this week, if it's not already there, before Thanksgiving. So you'll have a chance to come up with your list of, you know, these are issues that I want to make sure I understand so that we can address it. Questions? Suggestions? Also suggestions for what to do, how to structure this review. If you have views on this, please let me know. Okay, no other questions? Okay, so we are talking about probabilistic learning. So far, we talked about Bayesian learning. We understand what does it mean to be Bayesian. Specifically, we talked about naive Bayes, possibly the most important learning algorithm in this class. We talked about the independence assumption being made, and we gave a few examples for how to use these assumptions. And last time we talked about EM, and another very important algorithm, or family of algorithms, when you have some hidden variables. So I want to move on today to talk about learning more general probability representation of probability distributions. So we talked about, you'll see that we talked about some of these ideas when we talked about naive Bayes or in general about Bayesian learning, but it's going to be a little bit more general today. And specifically, we'll see that we have to come up with this notion of inference. We'll talk about two notions of inference as a way as a step in order to be able to learn representation of probability distributions. Okay, so so here is this is the area where we are playing. So we really talk about unsupervised learning nowadays. So we have a collection of examples. Think about them as these, in this case, n+1 tuples. There isn't a notion or a fixed notion of a class variable or a label as before, or one single variable that we want to predict or assign value to, but rather we see examples and we want to know something about the probability distribution. Perhaps we want to know something about correlations between variables. We want to know for a given event, an event that we didn't know we're going to be interested in ahead of time, possibly. But for a given event, we want to know what's the probability of this event and so on. So in order to do this, we need, given this data, to find a model that represents the data or that has generated the data, the most likely model that has generated the data. So let's think about what we've done so far here, right? So this is a model that we've already looked at, right? So while in general, the problem, as I'm going to show, is very, very hard, under some assumptions, for example, the naive Bayes assumptions, we actually solve this problem. So this is a graphical model or a representation of the naive Bayes case where we have a label, a variable that is our target label here, and then we have other variables that we call features. The assumption that we made is this conditional independence assumptions. Xi and Xj are independent given Y, the label. And under this, everything was simple. The question we're going to ask is, can we do this in more general cases, for more general probability distribution? So again, what have we done in naive Bayes? Again, under these assumptions, we didn't think about it this way. We thought about it as a classification problem, trying to classify Y. But if you really think about it, we figured out a way to represent the joint probability distribution, P of x1, x2, xn, and y. And this is how we represented it, right? And if you don't know how to go from here to here, think about it again. It's somewhere in the slides, but you should be able to do this. Essentially, what we have here is repeated use of the product rule, if you want, and then incorporating this assumption. So now, given that we know how to write this joint, we can compute the probability of any event. You want to ask me, okay, what's the probability of x1 being 0, x2 being 0, and y being 1? We can compute it. Here is one way to compute it, basically marginalization. I'm going to fix y to be 1, fix xy to be 0, fix x2 to be 0, and then marginalize over all the others, right? Which means I'm going to try all options, compute the probability because I know how to compute the probability of a complete event, and sum over this. This might not be the best algorithm to do it, although hopefully you agree that this is correct, right? Why isn't this the best algorithm to do it? Complexity? It's exponential. So how many things do I have to add here? 2 to the n minus 2, or something like this, or 3. I don't know, what did they say? N here. So it's n plus 1 minus 3 that I fix. So it's 2 to the n minus 2. I don't want to do it. But clearly, you can see that we can do this in a much better way, right? We have our assumption. We know that this model can be written this way, the joint, which means that I can write P of x1 being 0, x2 being 0, y being 1 as P of x1 given y, P of x2 given y, P of y given 1. Right? So again, product rule, Bayes rule, any way you want to think about it. So I don't really need to marginalize in this case. That's what makes this probability distribution so simple. Everything is easy here. And hopefully you're convinced that I can do this for any event or conditional event over these n+1 variables. Okay, so that's easy for the naive base case. The question is, what can we do in general? So in general, we want to do it for any probability distribution. The first thing you want to think about is that, how do I represent my probability distribution? And really, probability distribution is just a function that satisfies some property, right? So it's a positive function, and the sum over all the instance space is 1. That's it. Right? That's the only requirement you really need. So I can represent it many ways, right? So I can represent it as a table. Basically, I can list the probability of each instance. Let's assume that our instance space is Boolean, 0, 1 to the n. So I need a lot of numbers, right? The probability of each element there, and the last one I don't care about because it's 1 minus the sum of the others. It's a representation of a probability distribution. It's a little bit large, if n is large. Probably not good enough. And what we're going to do is we're going to make some assumptions so that we can represent the distribution in a more compact way. Still, there are many ways. So because probability distribution is just a function, I can represent it as a multilinear polynomial. Basically, think about multinomials, right? So a sum of terms where each term is a product of variables, right? Multivariate polynomial. It's just a function. We can do it. We can, and in fact, this representation has some nice properties that we're not going to get to. In particular, computing inference over this representation is better than over other representations. It has some other disadvantages. It's typically bigger than other representations. The two more common, for largely historical reasons, but there are also some good reasons, of representing probability distribution are Bayes nets, which essentially are directed acyclic graphs, and Markov nets, which are undirected graphs. And we're going to talk for the rest of today and next time only about directed graphs. As I said, you know, the undirected are also interesting, and polynomials or multinomials are also interesting. We're not going to go talk about it. So we already talked about one directed graph, which was this one. And we convinced ourselves that we can compute the probability of any event, and we want to be able to relax it. So we're going to move to graphical models, general graphical models, which, as I said, are called Bayes nets. So Bayes net can represent any joint probability distribution over a set of variables. The graph itself contains within it, or comes with, a set of independence assumptions. And we can write it multiple ways, and I'm going to say it multiple ways. Here is one way to say that what independence assumptions are hidden in my graphical representations. So given a graph that consists of nodes and directed edges, for every variable x, x is independent of its non-descendants given its parents. So just let's get the terminology right. So in this graph, z as an edge directed toward x, so we say that z is a parent of x. Y has a path that leads to x, directed path. So I would say that x is a descendant of y. And going back again to the assumption, x is independent of its non-descendants given its parents. So that's the assumption. With these conventions, we can always write the joint probability distribution this way. So this is the joint probability distribution. For no reason, I distinguished y here. It doesn't have to be a single y here, but I can write it this way. There is one node here that has no parents, P of y, times the probability, the conditional probability of xi given the parent of xi. Now, this is a theorem, and you should be able to prove this theorem. It's very easy to prove it. Essentially, all you have to do is you have to take this joint, make an assumption on an order. I suggest that you assume the order as the set of variables going away from y, or going towards y, from the leaves up or from this down, and then just write it down. Just factor this, and you'll use this assumption to get rid of all the other dependencies of xi. So xi is really going to depend on the parents. All these terms, the probability of xi given parents, in this case, x2 given y and z, x given z1, z2, z, and z3, x10 given z1 and z2, these are called conditional probability tables. So let's think a little bit about it. So, for example, what's the conditional probability z participates in? It's p of z3 given y. If I'm assuming only Boolean variables, it means that I have here two numbers, right? P of z being 0 given y being 0, and being 1 given y being 0. These two numbers sum to 1. And P of z3 being 0 given y being 1, and 1 being 1. Again, two numbers that sum to 1. What about this? P of x10. How many numbers do I need in these conditional probability tables? How many entries will this conditional probability table have? Why 4?
There's two values for z1 and two values for z2.
So I really need P of x10 given z1, z2, for combination of z1, z2. And for each combination, I need the probability of x10 being 0 and the probability of x10 being 1, two numbers that sum to 1. So really just 4 independent numbers, 8 numbers overall. Okay, and the same thing for here, right? So for x, I'm going to have 4 parents. So there are 16 options. So it's P of x given 16 options. Each two of them sum to, so it's 16 independent numbers. Altogether, 32 numbers. Okay, so that's the representation. So just to make sure we understand, this is the semantics. We have nodes that are random variables. We have edges that represent, you can think about it as causal influence, not necessarily causal in the kind of natural language meaning of causal. In fact, not causal in the natural language meaning of causal. And each node is associated with conditional probability distribution. Really, you can think about it as a data structure, basically a representation for a joint probability distribution, a compact representation, because if y is this compact, here I have 1, 2, 3, 4, 5, 6, 7, 8. If I really wanted to think about the complete joint, no assumptions, the number of parameters I will need here is 2 to the 8. And because I made some assumptions, if you look at all the sum of all these conditional probability distribution that we talked about, I will need a lot less now, right? So as I said, here we need 4, here we're going to need 16, here we're going to need again 4, 2, 2, 2, 2, 1. A lot less numbers. So basically just a compact representation. And you can also think about it as a representation that gives you some understanding of what are the independence assumptions. What are we assuming about the distribution? So let's take an example here to illustrate this better. So this is a classical example that we look at when we think about Bayesian network 101. Here's a story. Burglary alarm in your house rings when there is a burglary or an earthquake. An earthquake will be reported on the radio. If an alarm rings and your neighbors hear it, they will call you. Okay? So now we want to come up with a probability distribution that represents this. What are going to be random variables here? Yeah.
Alarm ringing.
Whether there is an alarm on or not.
Earthquake or not.
Earthquake or not.
Neighbors hearing it, calling you.
Yeah. For each neighbor a variable, whether they are going to call you, whether there is an announcement on the radio, and so on. Okay, so these are my variables. Earthquake, everything is binary. Yes or no. Burglary, alarm, yes or no. Radio, yes or no. Two neighbors. And then I want to come up with a set of independence assumptions. And the independence assumptions are encoded in my graph. So, okay, this is just the semantics. And these are the independence assumptions. So what am I assuming here? I'm assuming that alarm and radio are independent given earthquake. I'm assuming that given alarm, John and Marie calls is independent. I'm assuming that John is independent of earthquake given alarm, and a few other things that you can read off the graph, right? All these make sense, hopefully. And again, the reason I want to do it is because I want to have a more compact representation of the distribution. I want to learn less parameters. And again, the same question that I asked before, you can come up with the number 1, 2, 3, 4, 5, 6 variables. Complete probability distribution will have 2 to the 6 parameters. And think about this sparse network, how many parameters it will have. A lot less parameters. And just like the case before, when we talked about learning functions, less number of parameters, smaller space means better generalization. Okay, so these are the probability distribution that I want, right? So I want to know the probability of earthquake. This has no parent, so it's just probability of E being 1 or 0, probability of B being 1 or 0, conditional probability here, 4 numbers, 2 numbers here, and again, 2 in each one. So this is almost a tree, not quite a tree because of this, but a very simple, graph. So now, what is the representation of the joint? So I have 6 variables. The probability of an event is, and again, let's think about it. So first of all, I can write it as P of E given the rest times the probability of the rest. I can always do this. And I can keep on doing it. Now, notice that E is independent of anything else. So I can write P of E. B is independent of anything else. I need P of R given E here. I need P of A alarm given B and E, which is here. P of M given A, and P of J given A. So that's the joint. Again, convince yourself that I can always write a joint this way by keep on decomposing this, taking the assumptions into account. Okay, so once I have these assumptions, I can do everything. I have the joint, and just like we said before, give me any event. The probability if the joint called and the alarm was off, I can compute that. The probability the joint called and there was an earthquake, I can compute that. And any other event. Another way of writing these or expressing this independent assumption is through the notion of Markov blanket. So given a base net and a node X in it, the Markov blanket of the node is the following set of nodes: the parent of X, the children of X, and the parents of the children. Specifically here, if we look at earthquake, the blanket of earthquake are children are radio and alarm, no parents, but I have one parent of a child. So these three nodes are in the blanket. And essentially, the independence assumption can be rewritten as a variable is conditionally independent of everything else given the blanket. And again, this is often useful. Okay. So that's a quick introduction to BaseNet. And now the question is, so what? So what are we doing with it? So if we assume that this is an okay representation, the question is, or the two questions that come up is, okay, I want to learn this from data. Or at least one question is to learn this from data. What does learning mean? Learning could mean learn the structure, the graph itself. And learning could mean learn the parameters. And again, if you, in both cases, you can think about supervised learning of those parameters or unsupervised. And both of these problems are hard problems. And in fact, both of them are going to be guided by one principle. What will be the principle? The same principle we've been employing the last few weeks. I'm going to give you a graph, a BaseNet. And someone else will give you a BaseNet. And the question is going to be, which one is a better representation of the distribution? All you have to play with is you see data, and you can ask yourself which better represents this data. What would you do? Maximum likelihood, right? So you'll take each representation and compute the likelihood of the data given this representation. And because we don't have any other assumption, that's going to dictate which representation of distribution is a better representation for this data. So it's really maximum likelihood principle that is going to guide us. It's still going to be a hard problem. We're going to get to it at the end of today or next time. It turns out that in order to do this, we need to solve the inference problem. In fact, we care about the inference problem as an independent problem because eventually you want to compute probabilities of events. But as you'll see, you also need it in order to learn. And in inference, really, there are two distinct problems that we care about. One of them is computing the probability of an event. I'm going to give you the graph and the parameters, the BaseNet, and I'm going to give you a specific event, a set of variables, y, and an observation. Maybe I don't give you any observation, just a set of variables. And the question is going to be, what's the probability of this happening? Or what's the probability of y given that you've observed it? It turns out that this is a very hard problem. It's a Sharpe-complete problem. For those who know, it's a harder problem than NP-complete. It's the problem of, if NP-complete is the problem of solving satisfiability, given a CNF formula, what's the complexity of finding a satisfying assignment? Sharpe-complete is the problem of counting how many satisfying assignments a CNF formula has. So it's strictly harder. This is one problem we want to solve. The second problem that we may want to solve is finding the most likely explanation, or maximum posteriori assignment. It used to be called the MAP problem. Sorry, it used to be called the MPE, for most probable explanation. Nowadays, people call it MAP. So You'll see it in both ways. You just have to make sure which problem it is. And here the problem is, again, given the Bayes net, given an observation E, what is the most likely assignment to Y? It's a different problem, right? I don't care what's the probability of something. I just care about assigned values to Y such that this is the most likely assignment. It turns out that this is a much easier problem. It's only NP complete. And in many applications, this is really the problem that you may care about. Okay, so these are the computational problems, inference problems and learning problems. And what I want to do in the next few minutes is talk a little bit about inference and eventually get to learning the distributions. Okay, so I'm not going to be able to give you a complete algorithms. I'm going to try to convince you that you can write down the algorithm yourself for the inference. It doesn't mean that the algorithm is computationally easy. It's going to be computationally hard with some exceptions that we're going to talk about, but still it's going to be relatively easy to write down an algorithm. So in general, there are two broad approaches, right? One is exact inference, and I'm going to give an example algorithm for this. And a second in approximate inference. Given that exact inference is sharply complete, you may want to do approximate inference. In fact, approximate inference can also be shown to be NP hard. So there's no shortcuts here. These problems are difficult. But still, we may want to be able to do it. Questions so far? Okay, so we're going to start with a simple Bayes net. It's going to be a tree. The reason we care about a tree is twofold. One, because inference for trees is easy. Two, it turns out that learning for trees is also easy and actually quite interesting. So we're going to spend some time next time talking about how to learn probabilistic trees. Okay, but let's just talk about trees. So we're talking really about directed acyclic graphs where each node has at most one parent. Right? That's what makes it a tree. Again, the independence assumptions, each variable is independent of its non-descendants given its parents. In this case, X is independent of anything else given Z. V is independent of W given U, and so on. Okay? And given that, not only I can write this, the joint probability distribution is P of Y, which has no parents, times P of Xi given the parents of Xi, there's going to be a single node here. The set of parents is a single variable, which is going to make life easy. Okay. So really, for every edge, all I need to know is two numbers. Again, I'm assuming Boolean case here. P of X given Z, which means that Z can take two values. And I need to know P of X being 1 given any of these values. That's enough, because P of X being 0 is just 1 minus P of X being 1. And I need to know the prior for the root. Again, it's one number and 1 minus this number. Okay, so what I'm going to do now is I'm going to try to convince you that the inference problem is easy, and you can write it down. So given the tree, I want to compute the probabilities of certain characteristic events, and this will show you that we can do it. So we're going to start with what's the probability of P of X. Okay, so P of X is not given to me. What's given to me is P of Y and all the conditional probabilities here. And I want to know what is P of X. Think about it as P of X being 1. Okay? So how do I write this down? Basically, I want to be able to write this down as a function of the numbers I know, which are all the conditional probabilities. So what we're going to do is basically, we're going to climb up the tree because we know P of y. Eventually, we want to get there. So we're going to start by marginalizing. So P of x being 1, I can write always as I'm marginalizing and already use the product rule. So P of x being 1 given z times P of z being 1. P of x being 1 given z equals 0 times P of z being 0. So again, I know that most of you have seen this before. I want to make sure that you're fluent doing it. Won't be a problem. So now what do we know? I know how to compute this. It's given to me in the conditional probability table. I know how to compute this. I don't know how to compute P of z. It's not given to me. But the good thing is that I went one level up in the tree. So I can continue doing it until I get to the root of the tree. So recursively, I'm going to take P of z being 1, again, marginalizing over y. I'm going to get P of z being 1 giving y being 1 times P of y being 1. Same thing for y being 0. Now, I know this. It's part of the conditional probability table, but I also know this. Same thing for this term, so I'm done. So I climb up the tree. I can do this for z being 0. So what I have is basically everything in terms of the CPTs that I have, and the number of steps it took me is basically the number of steps it takes me needed to climb up the tree. So that's one type of event, P of single variable. So that's a linear time algorithm, in fact, in the depth of the tree. Now, another type of event I care about is P of x comma y, where x and y are two nodes with a path between them. Specifically, here y is the root, but it doesn't matter. So the same is going to... So for example, I care about P of x being 1, y being 0. And again, what I'm going to do is I'm going to start by conditioning this way, and then I'm going to walk along this path between x and y. So how do I do this? Go up the tree along the path from x to y. So I know P of y. I need to compute P of x given y. I'm going to marginalize using a node in between, z in this case, P of x given y and z times P of z given y. And I'm summing over all values of z. Now, what can I say about this? P of x given y and z. It's just like P of x given z. Why? Yeah, so here is where I'm using the independence assumption, right? So x is independent of y given its parent z. So I can get rid of this y here, and I get P of x given z, and that I know. That's in my conditional probability table. And I also have P of z given y, which I also know. So we're done. So again, this was a low depth tree, but the same principle is going to apply. I'm going to climb up the path using this independence assumption every time until I get to things that I know. Again, now I can represent everything in terms of the CPTs that I have, and P of y, which is here. The last type of event that I need to consider is variables that do not have a path from x to between them. So P of xu, where x is here, u is here, there's no direct path from x to u. However, it's a tree, so I know that they do have a joint parent. And I'm going to climb up to this joint parent, and this is how I'm going to compute the probability. So, for example, P of x being 1 and u being 0, I can always write it this way, right? given u times p of u. And now I'm climbing up to the joint parent. We always have one, right? It's a tree. So I'm marginalizing over y, p of x given u and y times p of y given u. What can I say about this? It's equal to p of x given y because given y, I don't care about u here, right? So y is an ancestor of x. Given that I know it, I don't care about u. So I can write this as p of x given y. Here I'm just copying p of y given u. This thing is something that we already computed, right? There is a path from x to y. It's the previous query that we solved. So I know how to do it. And we're done. So we reduced it to cases we've seen. So, okay, so I didn't give you a formal algorithm, but hopefully you see that inference for trees is simple. You can always do it. In fact, you can always do it in a linear time. So we solved it, right? So given a T, a tree with the associated CPTs, we showed, in quotes, that we can evaluate the probability of all events efficiently. There are more efficient algorithms. You know, you can do a lot of caching, you can do interesting things, but that's good enough for us to convince ourselves that the problem for trees is tractable. I really wanted to show you that you can do it yourself. Once you're confident using Bayes' rule and probability theory, it's done. Okay, so now for general Bayes nets, it's not going to be as easy. As I said, there are a couple of ways to think about it, and I'm going to give, again, without any proofs or anything, but give you an idea of how we do learning, how we do inference in general Bayes nets. I'm going to give you one way of how to do it exactly, and we'll talk a little bit about approximation, depending on time that we have. So one of the key algorithms that people think about is something that is called variable elimination. Now, it has to be clear, it's an algorithm. It's going to be a relatively simple algorithm. It's not going to make the complexity of the problem disappear, right? It's still going to be, worst case, Sharpie complete. But we're going to have a systematic way of computing the probability. So the example I'm going to use is computing the probability of this event, right? So this is the joint that I have. P of x1 up to xn is the product of P of xi given parents. I can always write it this way without knowing ahead of time. It could be that for some of the xi's, the set of parents is empty. So this is just an abuse of notation that results to P of xi. Okay, so, and I'm going to care about this. So we already know that the probability of x1 can be computed by marginalizing over all the n-1 variables, right? It's always true. So I'm fixing x1. You can imagine that what's written here is P of x1 being 1. So this is the sum of P of x1 being 1 and all the other x2 to xn. Take any value that you want. And I'm marginalizing over all these values. Okay, so 2 to the n minus 1 elements in this sum. Now, I can always also write it this way, right? So the product. Okay. So this, as I said, can be written this way, right? The joint is P of xi given the parents. And this sum, I can just write it sequentially. I choose an order. And when I'm marginalizing, first of all, I sum over values of xn, and then x minus 1, and then xn minus 2 up to x2. I didn't do a thing, right? The intuition in variable elimination is that I'm going to choose an order, hopefully good order, and I'm going to move irrelevant terms outside the summation such that the computation becomes simpler. And I'm going to cache intermediate results as I go, and if I chose the right order, or a good order, it's going to be simpler than if I chose a bad order, or than the worst case. That's essentially what we can say. OK, so let's take an example. So here is my Bayes net, a very simple chain graphical model, right? So A, B, and C are the nodes. And what are the conditional probabilities that I need in order to complete this representation of the Bayes net? You know. So I gave you the graph. The graph isn't the complete representation of the distribution. To really represent this as a distribution over the three variables, A, B, and C, I need a few conditional probability tables. What are they? P of C given B, the CPT over this edge, P of B given A, and P of A. Okay? That's sufficient for me to know everything I need to know about the probability distribution. And I want, for the exercise, to compute P of C. Okay? So we know that P of C can be written as marginalized over A and B of P of A, B, C. That's always true. Given the assumption, so this is always true, this equal sign. Given the assumption of this probability distribution, I'm going to decompose P of A, B, C as P of A, P of B given A, P of C given B. And you gave it to me, right? So these were the three CPTs that you just told me are needed in order to define it. So I know this. And again, I'm marginalizing over A and B. So notice that I can rewrite it in the following way. So P of C given B does not depend on A. So when I'm marginalizing, of course, I can change the order here, first A and then B. And I can move the P of C given B outside the A sum, because it doesn't depend. Basically, taking it out of the parentheses doesn't depend on A. You can always do this. If you need convincing, just write this down explicitly with all the values of A, B, and C, and see that you can take P of C given B outside the parentheses. Okay? So I can do this. Now, so far I've done nothing, right? Now I'm going to do something. Now, this guy, let's assume I instantiate A here. What does it mean? I'm going to have two numbers here. P of A being 0 times P of B given A equals 0, plus P of A being 1 times P of B given A being 1. So I'm going to have this sum. So this thing is a function of B, right? I just placed A there, and it becomes a function of B. I'm going to call this function FA of B. And I'm going to carry this. So I'm going to write now P sum over B, P of C given B, just copied, P of A given B. So essentially, I eliminated A from this, right? So I did it once, computed, instantiated A once, eliminated it. The rest of the computation, in this case, the rest of the computation is not so large, but still, you could imagine that there's going to be a little bit more, a few more sums there. I don't need to touch A anymore. I eliminated A. That's why we call it variable elimination. So now I saved some computation. Again, think about it, and you'll see that because I instantiated A, and it's not going to be a factor. Actually, I shouldn't use the word factor here. it wouldn't bother us in the rest of the computation, I simplify the computation. That's what we're doing. Okay, so really it's a sequential procedure. I'm abstracting what I just did for this simple example. I chose an ordering of the variables. This is the elimination ordering. For each variable v that is not in the query, I'm going to replace it with a function fv, where I instantiated it. And then I'm marginalizing v out, and I keep on going. Now, of course, the actual computation depends on the order. Because when I compute this f of v, I think this is kind of trivial if you think about how we defined it here. I could gain a lot, but maybe I will not gain a lot, because maybe A doesn't appear a lot of times and doesn't save a lot of computation. Okay, so let's go back to this, a slightly more complex network, and do variable elimination here. So again, here we have 6 variables. We wrote the joint probability distribution. Again, I remind yourself, so this definition, or this theorem, in fact, is something that I can directly read from the independence assumptions expressed in this graph, right? So the joint is P of E, which is here, no parents, times P of B, no parents, P of R given E, P of A, alarm given B and E, P of M given A, and P of J given A. That's always true. That comes directly from my assumption. And now let's assume that I want to compute this event, P of M and J given B. Now again, the way you read it, we never write this explicitly, but hopefully you understand that when I write this, what I mean is P of M being something and J being something, given B being something. Okay? I specified values for M, J, and B. I left E, B, and A, E, A, and R untouched. And I want to compute the probability of this. Okay, so really the computation is not that bad because I left only 3 variables untouched. But I want to run through the variable elimination and see how we do it in this case. Okay, so this is, again, the marginal. We need to know this. And that's what I want to compute, P of M and J given B. I can always write it this way, which basically shows you that all I need is to compute P of M, J, and B, because I can just normalize later, right? So computing conditional probability, in this case, is just like computing a joint, only that now it's a joint over a smaller number of variables, and this is where the complexity comes from, right? Computing the joint over a small number of variables, meaning marginalizing over a lot of variables, and this is where the cost is coming from. Okay, so that's the event I want to compute, which means I'm marginalizing over these 3 variables. So I have here a sum of 8 2 to the 3 variables, E, A, and R, E, A, and R. And now I'm just copying the joint, okay? So I know how to write this down. It's written here. So I'm writing this down. Did nothing so far. Now, since I have in the sum E, A, and R, I need to think about an order. So I'm going to choose an order. It's going to be R, A, and E. And once I chose this, actually I define the algorithm. So first of all, I'm going to eliminate R. That's what I said, right? Eliminating R means instantiate R. And R appears only once. So this is going to become a function of E, FR of E. which is this, right? Notice this is actually a sum of two numbers. P of R being 0 given E plus P of R being 1 given E. So it's a function, and I'm writing it replacing this. Okay, so this is one thing that I have. Now, next one is A. A appears in several places. Again, I'm instantiating it there. So I'm going to get P of A being 0 given this. Here I'm going to get P of J being given A to 0. And the same thing for 1. I'm going to get this function, right? So notice that it's sum over A, two values, of this function, the product of this, this, and this, which are all places where A appears. Okay? Now that I have this, I eliminated A. There's no A in my expression anymore. And finally, I'm eliminating E that appears in two places. Now, so it appears here, and it appears in one of the elements here. So these things are called factors. And really, if you think about it, what you want is you want small factors, because you want things that appear in a few places, so it's going to save your computation. So, okay, so the computation now becomes simple. You know, you basically, all you did is you kind of decided in which order am I marginalizing. That's it. You can think about what would happen had you changed the order of marginalization. It would take a little bit more computation because the size of the factors would be larger. Now, the complexity is still exponential. I mean, we've done nothing. We're just hoping that if we have good heuristics for deciding the order, then in some cases it's going to be better. As I said, worst case, it's not going to help. Okay, questions on this? Okay, so let's so next I was going to talk about Gibbs sampling. I'm going to just say something about it because I want to start talking about learning, just to give you the idea of what does it mean to do approximate inference without all the details. So, so far we talked about here is an event, and I want to compute the probability. So you can really think about it this way. So I have a universe here, and inside this universe I have an event, X, right? So these are, think about all these as this is your Boolean cube, right? 2 to the n different assignments. And X is an event that defines a subset of these, right? You know, for example, all those where x1 is 1 and x7 is 0. This is my X. And I want to compute the probability of this event. So essentially, I'm looking at this subset and computing this probability. You can think about it, if everything was uniform here, you can think about this problem of computing the probability as computing the volume of this weird thing here. Or we're in the plane, computing the area of this, right? That's basically the problem we're after. The only thing is that in general, not all the points are going to have the same weight. So it's a little bit harder than just computing area or computing volume, but it's really the same problem. So one way you can compute the area of this is sampling. What's the idea? If I give you a very weird area, and I ask you, compute like this X here, inside the Boolean cube, and I'm going to ask you, what's the volume of this area? How would you do it? Anyone thought about this problem ever? Yeah?
If you're doing a sampling type thing, you would just have and the number of dots that are outside.
So you're counting on the fact that given a point, you know whether it's inside X or not. If you have this oracle that tells you, it's really a counting problem or a sampling problem. So sample points from this universe. And for each point, decide whether use your oracle to tell you, is it inside X or not? And then you will approximate the area of X by the ratio of number of points that came out to be inside X to the overall number of points. Right? Everyone agrees that this is going to give you an approximation, better and better approximation of the area as the number of points goes up. And in fact, this is actually a very useful technique where you have this oracle, but the area or the shape of X is kind of weird. We don't have formulas to do it. By the way, this procedure also shows you one case where this is going to run into problems. When will this procedure run into problems? Yeah?
You need the points to be
In order to compute the area, yes, I need uniform distribution over the axis. In general, if it's not uniform, I need the sampling to be a function of this non-uniformity. So it should be a sample from the distribution. So imagine that there is some depth to this graph. Okay? The depth represents the weight of each point. I want the sampling to come from this graph with depth. So that's one thing. But when will it run into problems? If the area of X is tiny relative to the universe, you'll hardly see points there. And that's going to be an issue also when we approximate probability distribution. But anyhow, this is the idea, right? So rather than calling it a probability distribution, I'm calling it a function. And I'm going to sample these functions and compute the average of the number of points that I get from this function in my sampling. That's going to be my inference procedure. The only question is how to generate instances. And if we know how to generate instances, now, the instances have to come from my probability distribution. This is the comment that you had, right? So points that are more probable than others should come into my sample more often than others. So for example, if I want to compute the probability distribution P of X given E, conditional probability distribution, I want to generate instances that are consistent with E and are sampled according to X, really X given E. And the problem is, of course, I need a lot of examples to get good approximation. And more importantly, I have problems when E has low probability because I'm not going to see a lot of points in E that satisfy E. So the key idea of this, and this is kind of where I'm going to stop, is to use a Markov chain way of sampling things. So Markov chain is something that we kind of talked about when we talked about HMM. Think about sequences. I want to generate sequences of ABCs. ABC are going to be my variables. And Markov chain is going to define a tour over sequences of ABCs where the probabilities from one node to another are called the transition probability. They're going to tell me, okay, you visited B, you generated B, what are you doing now? With probability 0.1, you're going to generate another B. With probability 0.6, you're going to generate a C. With probability 0.3, you're going to generate an A. That's a Markov chain. It's a Markov chain because I'm assuming that independent of the time, the probability of generating being in xt plus 1 the probability of being at time t plus 1 at I, given that in ti was in j, is independent of t. Throughout the times, being in one state and moving to another is the same. It just depends on the I and the j. It does not depend on the t. That's why it's a Markov chain. And then there's a notion of stationary distribution of Markov chain. And again, so Pij is just a matrix that represents the transition probability from I to j. And I'm calling it here time-independent transition probability matrix, because it doesn't matter at what time I visited I, the probability of moving to j is the same all the time. And Q is the vector that represents my probability of being in state I. And it turns out that these processes have this property of stationary distribution, and this gives rise to an approximation inference algorithm. Essentially, what we're going to do is we're going to sample from this Markov chain repeatedly. Basically, we're going to go over this chain, and it can be showed that the distribution over the states converges to a stationary distribution, and this will allow us to get a robust estimation of our state distribution. So I'm not going to give the details. Okay, maybe the following example that will remind you what do I mean by Markov chain. So here is the following game that you can play with your friends. So take a stack of cards. Ideally, take more than just one. 52 cards, take 2 or 3. It's going to make this a little bit more robust. And let's assume that you define the following Markov chain. You choose a number, any number, 1 to 13. And when I start showing cards, you count the number that, say you chose 7, you count to the 7th card. You see the number, let's say the 7th card came out to be 5. Now you count 5 cards. The card that came out is 3. Now you count 3, and so on. So I define a chain. And the game is that you present this to your friend, you run along this chain for some time, and the question is, can you guess which number your friend has in mind now? Now, the number they have in mind is the last card that they saw in their Markov chain, right? And the answer is that it's very easy for you to do it. You choose a random number, doesn't matter what your friend chose, and you play the game too. Eventually, after some time, you're going to have the same number your friend has. The reason is that there is a stationary distribution. So play this game and you'll convince yourself that there is this notion of stationary distribution. You'll always be able to guess what number they have if you run it enough times. And the intuition is very simple. The intuition is that with some probability, at some point you'll collide. From that point, you're counting together. When they see 5, you see 5, and you count, and the next card that you observe is the same card your friend observed, and so on. So this is the idea of stationary distribution. This is the key idea that we're going to use when we want to do inference in BaseNet. So really our goal is going to be to sample from this distribution, and we're going to construct a Markov chain over the probability distribution and sample from the distribution that governs what we care about. So the rest is details. The details are actually quite involved, and I don't want to do it. You don't really need to do it, but the slides are here if you want to look at how this is done. And I gave a few examples here. I actually want to preempt what we're going to do next time, so you'll kind of think about it. So I want to talk about learning. So we talked about basenets. We talked about inference with basenets. and I want to talk about learning. And the question is, what is really the learning problem here? And that's kind of the thing that I want you to think about. So here is a tree, and I'm going to give you data. The data is assumed to be sampled from this probability distribution. What I want is for us to understand what does it mean that this data was generated. So it's a probabilistic tree. So different times I might see different data. Still, I want to be able to figure out what is the most likely tree that has generated this data. Right? Find the tree representation of this distribution. So when I say find the tree representation, you should be able to convince yourself that you have a well-defined notion of what do I mean here. And the well-defined notion is going to be the most likely one given the data. Right? So the probability, we know that the probability of the tree given the data is the probability of the data given the tree times P of the tree divided by the data. What I want to do is I want to find the most likely tree. Right? So assume prior distribution over the trees. The maximum likelihood approach is to maximize P of D given T, which is this. So far I've done nothing. It's really the same problem that we've done the last few weeks when we had coins or other probability distribution, right? I just used Bayes' rule, then I said, okay, so do argmax over this. The only question is, how do I do it? So two issues. One is, notice that given a tree, I need to compute P of each data item given this tree, which is the inference problem that we just solved. So now you know why I needed to talk about inference in order to talk about learning. So when we do learning, we assume that we know how to compute this. Okay? For each data item, I know how to compute this. And of course, I'm going to multiply over all data items, assuming that each data item was sampled independently from this distribution, and I'm going to argmax this. So that's, and again, using our assumptions, we're going to decompose it this way. And if you do it for naive Bayes, you will see that the probabilities that you learn for naive Bayes actually are going to lead you not only to the classification of Y in the most optimal way, but actually to the most likely distribution, joint distribution over this assumption, conditional independence assumption. So you can just write this down. So here is the thing that I want you to think about so that we'll be ready for next time. Here is a probability distribution over 4 variables. Here is another probability distribution. Well, almost. I need to give you the exact numbers that are here. Here is another probability distribution. What you want to think about is, are these probability distributions the same? And what does it mean for probability distribution to be the same? So you should be able to answer this question. You can ask another question, which is, given a sample, which of these three has generated the sample? Or, you probably want to refine this question, is more likely to have generated this? So these are the questions that we're going to talk about next time, and we're going to drive an algorithm that actually learns the most likely probability distribution. It's going to be an efficient algorithm for trees, or a little bit more general than trees, in a way that we'll define. Final questions? Okay, so see you on Thursday then. Hi.
About Malcolm blanket.
Yeah.
So it's the parents, children, and children and the parents.
No, parents of the children.
Parents and children.
Yeah.
But for
slightly different definitions of what I said. So in base net, you know, everything else given the descendants, not only the parents. That's one definition of the game. It's a little bit more general than just that. No. It's just different alternative definition of the same thing. So these two definitions are equivalent. So one says, look at the blending, which means immediate parents, immediate children, and parents of knowledge. And the other one talks about descendants, which is more than just parents. And it turns out that these two are equivalent. You can derive one from the other. No, it's not right. In fact, there are several alternative definitions. If you go to the text, you'll see that there are some other definitions that go through a notion of separation and stuff like that. I don't think it's so useful. But there are several definitions that are actually equivalent.
I'm not sure if I can finish the project for the Thursday
So, when can you finish? Okay, send it to me over the weekend, but try to send it over the weekend because I'm planning to write it, to read it over the weekend. So, yeah, if you send it Sunday, it will be good. Remind me that we talked about it also when you send it.